Hello there, this is Cody Jackson for Codamom, and today we are looking at the BIOS and UEFI on motherboards. So first we're going to talk about the BIOS because that is the foundation of everything that happens with computers, including the UEFI, which is built on the BIOS. So the BIOS stands for Basic Input-Output System. Basically what that is firmware, which is software on hardware, that controls and interfaces between the operating system and the system hardware. So basically you have software on a chip that acts as a middle layer between the operating system and the hardware on the motherboard or peripheral devices that handles the actual communications between the operating system and that hardware. If you've heard the term device drivers are basically the BIOS in that they drive devices based off of input from the operating system and other software applications. ROM chips on the motherboard, ROM is read-only memory. ROM chips should be hold, not whole, hold the initial boot software. On boot, additional drivers are loaded from the hard drive. So basically what happens is you have a chip on the motherboard, or several chips depending on the design, that hold the initial software that the computer looks for when it initially boots up. Once it gets past that initial boot phase, then other drivers are pulled from the hard drive and loaded into computer memory to allow access to other devices. System interrupts, which are called IRQs, interrupt request, allow the software to access hardware via the BIOS. So if a particular application wants to access, say, a sound card, it will send an interrupt request to the system through the BIOS, and that interrupt request is a request. It's a request from the computer software to the hardware saying, I would like to access this audio card. And based off of what the system is doing, it either allows it or it puts it into a queue, and at the particular time that it's able to release system resources, then the software is able to access that hardware. The BIOS and other drivers act as a standard interface between the operating system and disparate hardware. So it provides a common layer for programmers to program to that standard interface. So all you need to know is, I want to make a call to a sound card, but the developer doesn't need to know what model sound card that is, what features it has. All they're doing is just writing to a generic layer, and then that layer handles the different types of hardware that might be available. And this comes to the application programming interface. And for programmers, this is probably one of the most important things. We just talked about how it acts as a layer between operating system, applications, and hardware. And it provides a building platform to target, and you don't need to know the functionality of a particular device. You just write to the software API, and then that handles the communications to the hardware. If a particular feature is not available, then it just won't allow it to happen. But you, as the programmer, don't need to understand how that hardware works. The APIs a lot of developers are familiar with are particularly web applications. The REST API, for example, for HTTP protocols and stuff like that. So basically what an API is a black box for developers. And all the developer needs to care about is what goes into this black box and what type of data comes out so that they can use it. What's happening on the inside of this black box doesn't matter. And so that's why it can apply to hardware or software. The details of what's going on at that low level area of the hardware interaction or working with the software is irrelevant to the programmer. So that's it for the basics of what a BIOS is and how it works. We're going to talk about how a computer boots and how that uses the BIOS to do that. So the motherboard ROM contains all of the startup programs and the initial boot drivers for minimum functionality. So the BIOS is basically, without a BIOS, a computer is not a computer. It's a programmable toaster. The BIOS is what makes a computer able to do as much as it does. So you can have specialized computers that only do a specific thing, and that's because that BIOS is only designed for that specific thing. The computers that we all know and work with are considered general purpose computers. And so they have a BIOS that boots up to a generic operating system, allowing you to do anything with it. But there are specific computers out there, such as on the space shuttle or drilling, offshore drilling and stuff like that. Those are specialized computers that only do one job, and so their BIOS, their ROM, is going to have specialized boot up sequences, and it may not even load anything externally. It may all be on these chips, and that provides all of the functionality for that particular computer. So regardless, we move on to our list here. So post. As soon as you turn on the computer looks to the ROM and looks for the power on self-test. And what that does is it goes through and it tests all of the hardware that is connected to that computer prior to loading any software. If you hear beeps coming from your computer during boot, this is what it's doing, is that it's actually going through and it's testing your memory, it's testing your hard drives, it's confirming that you have a keyboard attached, checking that you have a monitor, all that type of stuff. And not only is it attached, but is it functioning correctly? If you really want to get into testing your computers, you can buy a post card which fits into a slot on your motherboard, and it will give you a display that shows you particular codes as the computer is powering up. And if you get an error on boot, you can take a look at that post card indicator and figure out what the error code is, look it up on the motherboard specification sheet, and diagnose, is it a problem with the memory or something like that. So after post, it goes into setup. So the setup is stored in the CMOS, which stands for complementary metal oxide silicon. And that's basically a dedicated chip that is non-volatile. It does not turn off with the rest of the computer. If you ever look at a motherboard and you see the little coin battery, that is the battery that contains, or I should say powers, the CMOS configuration files. So the CMOS is often confused with the BIOS. You may see people use them synonymously, but actually what happens is your CMOS is the configurations that the BIOS uses on boot to configure different things. So that may be your CPU speed. If you are an overclocker and you want to make your CPU faster, you go into the CMOS, change the settings, and the next time you boot, the BIOS sees those changes and tells the CPU this is the speed that you should be running at. It also handles the date and time for your computer. It allows you to turn on, turn off different peripherals, such as USB ports, such as PCI cards, networking, things like that. After checking the setup and configuring all of the hardware on the motherboard, then the bootstrap loader loads and finds the first physical sector on hard drive that holds the master boot record. From the master boot record, the computer finds what the first sector of a bootable volume is. Basically what that means is the ROM looks to find where the master boot record is, and the master boot record tells the computer where to actually start loading the operating system. So once that first sector from the bootable volume is found, the operating system kicks in and is pulled into memory, and then takes off and handles the rest of the boot process of loading the operating system. If you're confused about sectors and volumes and stuff like that, we'll cover that in a later video about hard drives and how they're formatted and stuff like that. But just recognize that when we're talking about sectors, we're talking about the smallest physical space that's allocated in a hard drive to hold data. So there are different types of ROM chips. And so we're going to talk about some of those. These ROM chips may apply to the BIOS. They may apply to other types of memory on a computer. Before we do that, I want to talk about ROM shadowing and why it's used. So a ROM chip is very slow compared to RAM, your normal memory that you use for your computer. So we're talking about 10 times slower than RAM for accessing a ROM, and that's just how the chip is designed. It's not designed to be very quick. Because running data off of the chip is so slow comparatively, the computer will take all of the data that's on those ROM chips, copy it into RAM, give it the exact same address that would be used to access it off of the chip itself, and so effectively that chip, it disappears. It's disabled from access by the operating system and other programs, so that whenever a program needs to access that ROM data, it will go into the RAM and pull it from RAM for faster access rather than actually going out to that chip and pulling that data out. So now we're actually going to take a look at some of the chips that are available for ROM, and we'll kind of go through the history of how these ROM chips developed into what we're using nowadays. So a mask ROM is basically designed like a traditional chip. The circuits are designed on a CAD program, computer-aided drafting, and all the circuitry is laid out. Then it goes through the photolithography manufacturing process, and it's etched onto the silicone. At that point, it can no longer be changed. What you have is what you have. If you want to change the data that's on that ROM chip, you have to actually change out the ROM chip. Assuming it's not soldered to the board, you can pull it out and put in a new one. So this particular picture shows one of Intel's original metal masked ROMs. This was used with the 8080 CPU, if you remember from our CPU discussion. And so this was the read-only memory that was provided with the 8080 CPU. And you can kind of see all of the individual little circuitry that was designed on here. And on the edges, a little bit hard to see in this picture. There's a better picture coming up. But you can see where there's connections coming in from the ceramic case to the actual pin connections that correspondingly go into the chip itself. Programmable ROM was a blank chip, so it did not have the etchings already on it, but it could be programmed later. However, it used a variety of different features to make it so that it was only programmable once. If you wanted a new configuration on your chip after it had been programmed, you would have to put in a blank chip again and reprogram it. So we'll take a jump to this website here, and so this is an anti-fuse ROM. And so anti-fuse just means that instead of having a fuse that is low resistance and burns out, it starts out with high resistance, and once you apply power to it, it creates a direct connection between 2 points. So instead of burning out and opening the circuit, it closes a circuit. So this is a blank chip right here, and this is these green bars are where the data is actually going to be written. And so here's the chip after it's been programmed. You can see how there's a bunch of little circuits that have been programmed into the system. And so if we look a little bit closer, so this section right here, the middle section of these two bands, this is what it actually looks like, where you have these anti-fused transistors, which are the green squares, and then the red rectangles are the storage elements themselves. So you have the transistor, and then you have the data that's actually going to be stored. And then, so when the chip is programmed, you have the dielectric breakdown and creates a connection between two locations, and that's what actually programs the chip. And then this here is just a photograph of a scanning electron microscope and what it looks like from an actual micrograph using a electron microscope. So back into the presentation. This is another demonstration of a PROM chip. So this one shows a little bit better how the connections are from the surrounding case of the chip to the chip itself. So this part here, the square in the middle, this is actual silicone on a gold foil base for the connections. And then these white bars that you see on the edges, those are the actual metal traces that go out to the ceramic casing of the chip holder, and that would go into the pins that are put into the motherboard. And then you have the metal connectors between the CPU silicone, or sorry, the ROM silicone, and these conductors on the ceramic case, and that's how the chip is able to communicate with the outside world. We've seen chips before. And so this is an older style that still uses gold connectors rather than the more traditional silver-looking aluminum ones. This is an erasable PROM, so has a little window that allows ultraviolet light to come in and touch the silicone. When the ultraviolet light touches the silicone, it actually kind of melts, for want of a better term, the circuitry in there and turns it into a blank chip so that you can reprogram it multiple times. And you can see that this is the physical connections that I was talking about on the other picture, coming off of the silicone here to the chip connectors, and then this white part here is the ceramic case that has the actual pins coming off of it that are connected to the motherboard. And you see over here, this is the first Intel erasable programmable ROM from 1971. What we use now is electrically erasable PROM, or double EEPROM, or also called flash ROM. It does not require UV light. It's just updated via software. At this point, it's really just kind of a generic chip that allows you to flash the software that's going to be put onto that chip. This one is just a flash memory integrated component surface mount technology, so it doesn't have pins that fit in a socket. It's actually soldered directly to the motherboard itself, as you can see. And there's nothing that you can really see with it. If you want to change the software that's on this chip, all you have to do is just download the software, run the update process, and that chip has now been reprogrammed. So that's it for the BIOS. We're going to talk briefly about the UEFI and how that differs from the BIOS. So UEFI stands for Unified Extensible Firmware Interface, and basically it's just an improvement on the BIOS. The BIOS has been around since the 70s. It never left that 1970s frame of mind in terms of small data sizes, small memory access, and minimal functionality. So a BIOS is limited to 128K, text mode only. There's no space in the ROM for additional diagnostic software, simple programs like a web browser or a text editor to read documentation or to find some information in case you need to be troubleshooting. And the BIOS only works for MBR, master boot record, formatted drives, maximum of 4 partitions, and basically a maximum size of about 2 terabytes. Now we have individual hard drives that are greater than 3 terabytes, and so it's not working for us anymore. So the UEFI is basically a layer on top of the BIOS, and it replaces a lot of the functionality that the BIOS provides, such as the bootloader and your runtime services that run during operation. It gives you some enhanced versions of pre-boot functionality and additional applications such as web browsing, email support, things like that, so that you can do some diagnostics without actually booting the computer into an operating system, say if you have a bad hard drive. It also supports 128 partitions of nearly 9.5 zettabytes, where 1 zettabyte is a billion terabytes. So basically, at this point in time, there is no way that you are going to fill up as much hard drive space as the UEFI supports. So that's it for this video. We talked about the basics of a BIOS. We explained what the API is and how it provides a solid layer of programming for a developer to write towards without caring what's below that layer. We discussed the different boot processes, we explored different ROM chips, and explained how the UEFI improves on a BIOS. In our next video, we are going to talk about memory, particularly random access memory, which is what we all use in our computers, but just kind of how memory works in computers and things like that. So once again, I hope you enjoyed this video. I hope you learned something. If you have any comments, questions, concerns, please let us know in the comments. Until next time, keep learning and have fun. Thank you.